So we're going to continue our discussion of acetals and ketals and looking at their practical utility a little bit. What I want to just mention briefly is that cyclic acetals and ketals can be protecting groups for dialcohol substrates too. Now, in particular, we've got a specific class of dialcohols, 1,2 diols, or vis diols. Now, vis refers to within the same vicinity. So this is actually short for the 1,2 diol. It's a little bit awkward nomenclature, but as opposed to there's another one called like gem and that sort of thing. But we'll stick with 1,2 diols or vis diols. Okay, so these are basically like complex. You want to think about these as like complex ethylene glycols. For the ethylene glycol, that was when we had an OH on the CH2 to an OH. Okay, so let's look at an example of this. Let's say we've got this molecule with a bromine here, okay, and we want to do a Grignard at this position. So at the carbon atom that I've labeled, it's got a bromine, so it seems like it should be good to make a Grignard reagent, right? Well, if we add the requisite magnesium to that, what we form is a magnesium bromide, our Grignard reagent, but in the presence of an alcohol. 2 alcohols, in fact. So we would say that these alcohols are not compatible with the basic Grignard reaction or the Grignard reagent. Now, the reason why that is because Grignard reagents are highly basic and they react with alcohols. If you recall from the Grignard reaction in Organic 1, maybe you don't recall much, it has been a while. Hopefully, hopefully you remember it. But if you don't, you may remember in big words, this was the lab I wrote in big words on the board, don't introduce water. No water should be present. There can't be any water in this reaction, okay? I guess for, maybe, I can't remember if we did this one for the COVID-19 semester, maybe not. Anyway, for a Grignard reaction, we cannot introduce water. We cannot introduce anything with an OH because it will just react and neutralize the Grignard reagent, killing the Grignard reagent. So what do? Let's, quote, protect the alcohols. Now, if the alcohols are in the position that they're in, if you notice, they kind of look ethylene glycol-y, and that's just the 1,2 diol or the vis diol. If you look, it's just like a complicated ethylene glycol. And so what that means is we can actually make a cyclic ketal using it. It's just a different way of looking at the cyclic ketal reaction. That is what I want to do first is I'm going to take my complex dialcohol and react it with a super simple carbonyl, like acetone. I mean, we have bottles of acetone lying around. Okay, so what I'm going to do is react these 2 things together, and yes, the bromine's down here, in the presence of H+, and perhaps I have an excess of my acetone because acetone's easy to come by. What that means is that our dialcohol will no longer be a dialcohol. It will react to form a cyclic ketal. So what I'm going to do is highlight the cyclic ketal here. And there's that bromine. We have the cyclic ketal, and then if we look at the atoms that were once acetone, I can do those in red. There's our acetone carbons, and there's our cyclic ketal. So it's the exact same chemistry. It's the exact same reaction that we looked at last time, except we're looking at it from the perspective of the alcohol. We have a complicated alcohol that we want to protect and do a Grignard reaction on at a site that would otherwise react with the 2 alcohols. Okay, and we could do this on either side of the Grignard reagent. just as long as we have two alcohols that are within proximity of each other like this, a 1,2 dialcohol, this will work really well. You can separate them into 1, 3 and make 6-membered rings, but I just want to keep it to 5-membered rings. That makes it simpler. Well, anyway, at this position, now we have a protected dialcohol, and that's technically called a diol, but I don't want to worry about nomenclature at this point. So when we react this with magnesium 0, what we get is a Grignard reagent that is stable enough to do a Grignard reaction. I'm just going to write happy Grignard reaction. And I don't know what happens to the magnesium bromide. It reacts with something in a Grignard reaction type of fashion. Let's just say it's an R group. Hooray, right? Well, not quite. We have to remember that the deal with the protecting groups is they're a masking group too. We can put the mask on, but we have to be able to take the mask off. Otherwise, they're kind of useless to us. Otherwise, we've changed our identity. So we need to demask our substrate. And to do that, what we do is add an acid catalyst and an excess of water. It's the exact same conditions that we've looked at before. It's just now that we're worried about the alcohol, not the carbonyl. And so what that's going to do is go back to the dialcohol plus our carbonyl, and our R group's been installed by way of the Grignard reaction. So we protect, do our chemistry, deprotect or unmask. So this is going to be our deprotection, removal of the protecting group, or unmasking. Hopefully I don't think I've used the term deprotecting in the last lecture, but hopefully it's not too far of a stretch. It's just removal of that protecting group that I said has to be able to be removed if we're going to be able to put it on and take it off. If we're going to put it on in the first place, we have to be able to kind of take it off and remove it. Okay, what I want to mention briefly, because it does open up the door to some other types of chemistry, is sulfur variance on thioacetal, sulfur variance on acetal and ketal chemistry. Okay, so in sulfur variance, what we do is we make ThioKetals and ThioAcetals. So thio just means sulfur in place of oxygen. Sorry, new page here, new page alert. Okay, so what we do here is we take our ketal structure and we replace the oxygen atoms with sulfur. And we could do that for the acetal as well. So thio or thia means replace O with S. And S is in the same group of the periodic table as O. So it's usually not that big of a deal in terms of understanding the chemistry to replace the two. Okay. So in particular, what we like to do is make thioKetals or cyclothioacetals. So cycloketals, ketals are particularly useful. Okay, so in that case, what we do is we take the ketone, and I'll show you those conditions here in a second. But we convert that into a sulfur variant of our cyclic ketal shown here. So this is a cyclic thioketal, and we could do the same thing on the acetal if we needed to. Now it turns out that this is useful because this can be removed. Thioketals can be put on and removed. Remember, we need to be able to do both of these if we're going to use this as a masking group under different conditions than normal. I'll just write normal ketals here. And what I mean by normal is the oxygen ketals. Okay, so what are those conditions? Well, you use a, oh, I'm so sorry. You use a BF3 Lewis acid. And then if you want to go backwards, I believe it's H2O and HgCl2, H2O and mercury dichloride. So BF3 will work on the top to make your cyclic ThioKetal, and then removal, you use mercury and water, but you use water again. Okay, and I guess for the addition, what we need is we need that sulfur variant of ethylene glycol. Turns out that sulfur versions of alcohols smell real bad. That's not pertinent to the lecture, but it's worth mentioning. So this does smell really bad. I mean, worse than like rotten eggs. It makes rotten eggs look like, I don't know, pansies or something that smells nice. I don't know. I've smelled them. I know too well what they smell like. So not only do they smell bad, but our limits to detection are phenomenal. Like, holy cow, we can smell these things like we can detect them at like parts per trillion levels, which is terrible. Like, why can't we detect the good smelling things at parts per trillion levels? Why is it just a single like molecule per trillion of all the other molecules floating around us, a single molecule that we can detect? So for example, if you put a butane SH, so like take butanol and replace the OH with an SH, or no, better yet, ethanol. If you take ethanol and put an SH instead of an OH, man, we can smell that so well, and it smells so bad. And because of that, what we do is we load it up in, well, not load it up, we use small amounts of it in our natural gas supply so that we can detect leaks. Turns out that, you probably know this, the natural gas is odorless, but we add a bunch of sulfur containing things to it because we have this parts per trillion level, and we're not gonna be thrilled to smell that stuff. And so we're gonna deal with a gas leak right away if we have one, which has obvious safety ramifications. Okay. One time I ordered ethane thiol. I needed it in a chemical reaction in grad school. So it's the stuff that we add to gas, okay? So it smelled so bad that when they packed it in the warehouse, even though they did everything right, you could still smell it on the packaging on the shipping container. So the day that it was delivered was the day that we had a bunch of people walking around in hazmat suits because looking for the gas leak. And I was like, oh, that's my chemical. And so I immediately put it in storage where you couldn't smell it, and I had to apologize to people. I mean, I did nothing wrong. I just ordered this stuff. They had to pack it better. Anyway, it happens. People deal with it. It's better to have the hazmat suits out and ready to go as opposed to, not knowing where they're at. Okay, anyway, so you got this. What are you going to do with it? What are you going to do with this chemistry? The complementary conditions, I think, are the useful thing. So what I'm going to do is show a scheme where, let's say we've got a cyclic acetal. What you can do is you can add the dithio alcohol, ethane dithiol, dithioethane, dimercapto, whatever. Okay, let's not worry about the nomenclature. And so you can form the cyclic ketal on the ketone that's present, and that's not going to touch the oxygen-containing acetal. And so you get this species. And then what you can do is you can add H plus and H2O. Now these are the conditions to revert a cyclic acetal or ketal back to the carbonyl, but this won't touch the ThioKetal or the ThioAcetal because that requires mercury. Okay, so what that's going to do then is unveil, in this case, an aldehyde, and leave our thiocyclic ketal alone. We can do some chemistry. We know a lot of aldehyde chemistry so far. I mean, we've got more to learn, but we can do some chemistry, and I'm going to convert that aldehyde into an R group. And let's say that chemistry was reactive enough to react with both a ketone and an aldehyde. A lot of stuff that can react with ketones will also react with aldehydes, and mostly vice versa too. So that would be a concern, having that ketone present. So having it protected as the cyclic ThioKetal is helpful. We can then add H2O and HgCl2 to get back our ketone. Again, highlighting that those are formed and removed under complementary conditions. I mean, you need water in both cases for the removal, but you need a different thing to pull off the sulfur, pull off the oxygen. Okay, so fun little digression, I guess, into the smell of certain compounds. And you can actually become chemically desensitized to it, which happened to me. So I couldn't detect them as well, which you're like, oh, great, blessing in disguise, except when you're working with them and they're kind of toxic and you can't pick them up. You look around and you're like, wow, why is everybody else vomiting around me? Okay, anyway. All right, have a good one, everybody. We'll end here. We'll see you next time for the next lecture.